Hello Stat 200. Welcome to the full video lecture for Lesson 9, Inference for Two Samples. In this lesson, we are going to learn how we can use the z-distribution to construct confidence intervals and to conduct hypothesis tests to compare the proportions of two independent groups, and how we can use the t-distribution to construct confidence intervals and conduct hypothesis tests to compare the means of two independent groups. We have 3 learning objectives this week. One thing I'd like to point out here is that we are really emphasizing Minitab Express from here on out. In this lesson, I'll show you how to use the formulas and some quick examples using summary statistics, but whenever possible, you should use Minitab Express. This is an outline of what I'm going to cover in this video. First, I'll go through all of the procedures associated with two proportions. Then, I'll cover the same points with two means. Let's get started by looking at the assumptions that must be met to use the z-distribution when we're comparing two proportions. When all of the following conditions are met, the sampling distribution will be approximately normal. Here, these conditions are written in terms of the population parameters. When we're constructing a confidence interval or conducting a hypothesis test, we don't know the population parameters, so we estimate them with the sample statistics. Note that these are really equal to the number of successes and the number of failures in each group. So in order to approximate the sampling distribution with the z-distribution, when we're comparing proportions from two groups, either with a confidence interval or hypothesis testing, there needs to be at least 10 successes and at least 10 failures in both groups. What if this assumption is not met? Here's a flowchart that you can use. If the assumption is met and there are at least 10 successes and at least 10 failures in each group, then you use the z-distribution. Minitab Express will call this the normal approximation method. This is the procedure that we'll be focusing on this week. If this assumption is not met, then you have two options. You can use the simulations that we learned in lessons 4 and 5. Recall we learned how to make a bootstrap confidence interval using StatKey, and we learned how to conduct a randomization test in StatKey. Or, your second option is to use Fisher's exact method, which is based on a binomial distribution. We are not covering this method in this course. Assuming that this assumption is met, and there are at least 10 successes and at least 10 failures in each group, this is the formula for the standard error for the difference in two proportions. We won't have the population proportions, so we'll estimate this using the sample proportions. The sample proportion that is used will vary depending on if we're constructing a confidence interval or computing a test statistic. When constructing a confidence interval, we'll use the sample proportions from each group. When conducting a hypothesis test, we're working under the null hypothesis, which states that the two population proportions are equal. That's why this formula is different from the one above. Here, p hat is the pooled estimate of the proportion. It's essentially the proportion overall, ignoring that there are two groups, or under the assumption that the two groups have the same proportion. I'll walk through an example now of computing the standard error using both of these formulas. Here's our scenario. In a sample of 100 shoppers at store A, 75 were women. In a sample of 80 shoppers at store B, 50 were women. Estimate the difference in the proportion of all shoppers at the two stores who are women with 95% confidence. If we're estimating the difference, that means that we're constructing a confidence interval. We'll start by checking the assumption. We need to have at least 10 successes and at least 10 failures in each group in order to use the normal approximation method. We're estimating the difference in the proportion who are women. We'll call store A group 1. At store A, there were 75 women in the sample. The sample size for store A was 100, so that means that 25 people at store A were not women. We'll call store B group 2. At store B, there were 50 women in the sample. The sample size at store B was 80, which means that there were 30 people at store B who were not women. These values are all at least 10, so this assumption is met. We can use the normal approximation method here. Let's move on to compute the standard error. Here is the formula that we use to compute the standard error for the difference between two proportions when we're constructing a confidence interval. For this scenario, we're estimating the proportion of customers who are women. For group 1, which is store A, the sample proportion is 75 over 100, which is 0.75, and the sample size is 100. For group 2, which is store B, the sample proportion is 50 over 80, which is 0.625, and the sample size is 80. We plug these values into the equation, and the standard error that we would use when constructing this confidence interval is 0.06932. Let's do one more example, but for a hypothesis test. In a sample of 100 shoppers at store A, 75 were women. In a sample of 80 shoppers at store B, 50 were women. Test for the difference in these two populations' proportions. We have the same sample data here, but now we want to conduct a hypothesis test. The assumption is still the same. We need to have at least 10 successes and at least 10 failures in each group. The procedure for checking the assumptions is the same for confidence intervals and for hypothesis testing. What's going to change slightly is the formula for the standard error. Here, we need to start by computing the pooled proportion. That is p hat. Note that when I plug these values into the equation, I enter the sample proportions as fractions. I do this because the sample sizes then cross out, which makes the math a little bit simpler. If you look closely at what we're doing here, we're really finding the overall proportion. So if there's no store A and no store B, and we just had 180 customers, 125 out of those 180 were women. Next, we use this pooled proportion to compute the standard error. We plug these values into our formula, and our standard error is 0.06912. Note that this is very similar to, but not exactly the same as, the standard error that we computed when we were constructing a confidence interval. Next, we are going to construct a confidence interval to estimate the difference in two proportions. I'll show you the formulas and go through a quick example, but whenever possible, you should be using Minitab Express. We're still using the same general form of a confidence interval. Our sample statistic is the difference in the two sample proportions. Assuming assumptions are met, our multiplier comes from the z-distribution. And the standard error formula that we saw earlier for a confidence interval is the last piece here. I'm going to use the example that we just worked with when we computed standard errors. We already checked that there are at least 10 successes and at least 10 failures in each group. And we computed the sample proportions and identified the sample sizes. The only other piece of information that we need here is the z-multiplier. This is a 95% confidence interval. The z-multiplier will be the values that separate the middle 95% from the outer 5% of a z-distribution. I'll take you to Minitab Express now to find that value. I'm going to construct a probability distribution plot to display probability. The default is a z-distribution. That's a normal distribution with a mean of 0 and standard deviation of 1. If 95% is in the middle, then we have 5% split equally between two tails. Select equal tails and confirm that 0.05 is split between the tails. Our Z multiplier is 1.95996. You'll often see this rounded to 1.960. We plug these values into our equation, and we get a 95% confidence interval of negative 0.011 to positive 0.261. To interpret this, I am 95% confident that in the populations, the proportion of store A shoppers minus the proportion of store B shoppers who are women is between negative 0.011 and positive 0.261. Next, let's do an example using Minitab Express. We'll use this scenario. Data concerning cigarette smoking were collected from a sample of 362 college students. Out of 193 males, 27 were smokers. Out of 169 females, 16 were smokers. Estimate the difference between the proportion of all male and all female students who are smokers with a 95% confidence interval. The first step is to check the assumption. There must be at least 10 successes and at least 10 failures in each group. Group 1 will be the males and Group 2 will be the females. In Group 1, there were 27 smokers, which means that there were 166 non-smokers. And in Group 2, there were 16 smokers, which means that there were 153 non-smokers. All of these values are at least 10, so this assumption is met. We will use the normal approximation method. I'll take you to Minitab Express now to show you how to do this. I'm on a PC, so I'll go to Statistics, to Samples, Proportions. If you're on a Mac, it's very similar. It's Statistics, to Sample Inference, Proportions. The default in Minitab Express is to use raw data. In other words, to have your data in the worksheet. In this scenario, though, we have summarized data. Group 1 was the males. There were 27 smokers out of 193 males. Group 2 was the females. There were 16 smokers out of 169 females. Under Options, the default is a 95% confidence interval. The last drop-down here is Test Method. For a confidence interval, we are estimating the proportions separately. This is the default. Recall the two different standard error equations that we saw earlier. For confidence intervals, we estimate the proportions separately. For hypothesis testing, we use the pooled proportion. So for a confidence interval, you do not need to change the default test method. Click OK. Here is our 95% confidence interval for the difference in the two population proportions. Negative 0.020681 to 0.111125. To interpret this, I am 95% confident that in the population, the proportion of males who smoke minus the proportion of females who smoke is between negative 0.021 and 0.111. Next, I'll do an example using raw data. I'm going to use a data set that comes with the Locke textbook. You can find this on their website. The data set is called ICU Admissions, and you'll want the MTW file. We want to construct a 95% confidence interval for the difference in the proportion of males and females who had an infection. In this data set, in the column labeled sex, 0 equals male and 1 equals female. And in the column labeled infection, 0 equals no infection and 1 equals infection. Again, I'll go to statistics, to samples, proportions. If you're on a Mac, it's statistics to sample inference proportions. The default is that we have both samples in one column. That is the case here. What that means is that we have one column with a response variable, which Minitab will call samples. That's the infection column. The event that we're calling a success is having an infection, which is infection equals 1. And we have one column in our data set that is the grouping variable, which Minitab calls sample IDs. That is the sex variable. Under options, we'll keep the default 95% confidence level, and for a confidence interval, we estimate the proportions separately. Click OK. Here is our 95% confidence interval. This is the proportion of males minus the proportion of females. I'm 95% confident that in the population of all ICU patients, the proportion of males with an infection minus the proportion of females with an infection is between negative 0.164054 and positive 0.118213. Next, we're going to move on to hypothesis testing. We'll be using the same 5-step hypothesis testing procedure. Step 1 is to check assumptions and write hypotheses. This is our flowchart for checking the assumption. We need to have at least 10 successes and at least 10 failures in each group in order to use the normal approximation method. This is the method that we're focusing on this week. If this assumption is not met, then we would have to use the simulations that we learned back in lessons 4 and 5, or you could use Fisher's exact method, which is not covered in this course. Then we write hypotheses. This chart is from the online notes. It shows all of the possible hypotheses. Note that these could also be formatted like this. Step 2, compute the test statistic. That will require a set of 3 equations if you're doing this by hand. Whenever possible, I strongly encourage you to use Minitab Express. We'll see an example shortly. You'll see that the hand calculations require a lot of steps and take a lot more time than using Minitab Express. Step 3, determine the p-value. This is the area under the z-distribution that is more extreme than the test statistic in the direction of the alternative hypothesis. We'll need to use Minitab Express to look up this area. Step 4, make a decision. If the p-value is less than or equal to the alpha level, which in most cases is 0.05, we reject the null hypothesis. If the p-value is greater than the alpha level, we fail to reject the null hypothesis. And step 5, state a real-world conclusion. If you reject the null, the results are statistically significant, and there is evidence of a difference in the population. If you fail to reject the null, the results are not statistically significant, and there is not evidence of a difference in the population. Let's work through some examples. I'll start with an example by hand using summary data, then we'll go to Minitab Express, which is the preferred method. Here's our scenario. Are patients given treatment A more likely to report improvements than patients given treatment B? Here, our data are presented in a 2-way contingency table. Within treatment A, 40 out of 50 reported an improvement, and within treatment B, 35 out of 50 reported an improvement. We're using the 5-step hypothesis testing procedure again, and step 1 is to check assumptions and write hypotheses. Assuming that an improvement is considered a success, there are 40 successes in the first group and 10 failures, and in the second group, 35 successes and 15 failures. These values are all at least 10, so we can use the normal approximation method. Next, we need to write our hypotheses. We're comparing two population proportions. The null will be that the two population proportions are equal. We want to know if there are more successes within treatment A, which is group 1, so this will be a right-tailed test, given that A is group 1 and B is group 2. Step 2 is to compute the test statistic. The calculations for this can get a bit complicated, which is why we recommend that you use Minitab Express whenever possible. I'm going to try to color code the equations for this example, so hopefully that will help you follow along with each step. This is the formula for the Z test statistic. It follows the same general form of a test statistic. In the numerator, we have the sample statistic, which is the difference in the two sample proportions. Sometimes you'll see this with a -0, signifying that the null parameter here is 0. A lot of times, though, this is left off. And in the denominator, the standard error. This is the formula for the standard error. And within this, we have the formula for a pooled proportion. So you can see that there are going to be quite a few steps to work through to get to this test statistic. We're going to start with the last equation here. For this, we need the sample proportions and the sample sizes. Again, we're going to call treatment A group 1. P hat 1 is 40 over 50. N with a subscript 1 is the sample size for group 1. That was 50. P hat 2 is the proportion of successes in group 2. That's 35 over 50. N with a subscript 2 is the sample size for group 2, and that was also 50. These are all of the values that we need to compute the pooled proportion. Remember, I suggest keeping the sample proportions as fractions for this, because when you multiply the sample proportion by the sample size, you'll get the number of successes again, and it prevents you from having to work with more decimals than necessary. When we do out the math here, we get a pooled proportion of 0.75. Another way to approach this would be to compute the proportion of the total successes, ignoring the two groups. Total, there were 75 successes out of a total sample size of 100. Next, we can compute the standard error. We plug the values into our standard error equation. And we end up with a standard error of 0.0866. Now we can compute the Z test statistic. Again, we plug our values into this formula. In the numerator, we have the difference in sample proportions, and in the denominator, the standard error that we just computed. We end up with a test statistic of Z equals 1.155. All of that was step 2. At this point, I hope you're convinced that using Minitab Express is a much better option than doing all of these calculations by hand. Step 3, determine the p-value. Looking back at step 1, we have a right-tailed test. Our p-value will be the area under a z distribution to the right of 1.155. I'll take you to Minitab Express now to find that area. I'm going to construct a probability distribution plot to display the probability. The default is a z distribution. That's a normal distribution, mean of 0, standard deviation of 1. Our test statistic is a specified x value. This was a right-tailed test with a test statistic of 1.155. Our p-value is 0.124045. Step 4, make a decision. Our p-value was greater than the standard 0.05 alpha level we fail to reject the null hypothesis. Step 5, state a real-world conclusion. There is not evidence that in the population, patients given treatment A are more likely to report improvements than patients given treatment B. Next, I'll take you to Minitab Express to show you how this same example could be worked through there more efficiently. Again, I'll go to Statistics, 2 Samples, Proportions. If you're on a Mac, it's Statistics, 2 Sample Inference Proportions. We have Summarized Data. Sample 1 was treatment A. There were 40 successes out of 50. And sample 2 was treatment B. There were 35 successes out of 50. Under Options, the default is a two-tailed test, but we have a right-tailed test here. The confidence level doesn't matter since we're not using the confidence interval here. The test method we do need to change. Recall for hypothesis tests, the null is that the two proportions are equal, so we use a pooled estimate of the proportion. Click OK. Minitab Express, by default, runs 2 hypothesis tests here. You can see the first is Fisher's exact method. This is based on the binomial distribution. You can use this if the assumption of having at least 10 successes and at least 10 failures in each group is violated. When that assumption is met, though, the normal approximation method is often preferred. For this test, our z-test statistic was 1.15, and our p-value was 0.1241. Those are steps 2 and 3 of the 5-step hypothesis testing procedure. Steps 1, 4, and 5 would be the same as they were when we just did this example by hand. Let's walk through one more example. I'm going to use the ICU admissions dataset from the Lock 5 textbook again. Let's say that I want to compare males and females in terms of whether or not they were at the ICU following a surgery. I want to know if the proportions are different. Step 1 is to check assumptions and right hypotheses. In order to check the assumption that there are at least 10 surgeries and at least 10 non-surgeries in each group, I'm going to run the test here in Minitab Express to get the descriptive statistics that we need to check the assumption. The sex variable here is coded as 0 equals male and 1 equals female. The service variable is coded as 1 equals surgery and 0 equals other medical treatment. I'll go to Statistics, 2 Samples, Proportions. Both of our samples, in other words, the males and the females, are all in the same columns. Samples are the response variable. This is service. We want to compare the proportion who had surgery, so that means service equals 1. The sample IDs is the explanatory or grouping variable. That is sex. Under Options, we want to know if the proportions are different, so this is a two-tailed test. The alternative hypothesis here, the default method, is correct. We're not going to use the confidence interval, so we can ignore the confidence level, but the test method we do need to change. For hypothesis tests, we use the pooled estimate of the proportion. Click OK. In the descriptive statistics, males were coded as 0. There were 124 males in our sample. 70 were there following surgery. This means that 124 minus 70 did not have surgery. That is 54. Females were coded as 1. There were 76 females. 37 were there following surgery. That means that 76 minus 37 did not have surgery. That equals 39. These values are all at least 10, so we can use the normal approximation method. We scroll down. Minitab Express has written out the hypotheses here. So we've completed step 1 of the 5-step procedure. Step 2 is to compute the test statistic. Assumptions were met, so we're going to use the normal approximation method. Our z-test statistic is 1.07. Step 3, determine the p-value. That's 0.2851. Step 4, make a decision. Our p-value is greater than the standard 0.05 alpha level. We fail to reject the null hypothesis. And step 5, state a conclusion. There is not evidence that males and females who are in the ICU differ in terms of whether or not they are there due to surgery. We have just covered all of the content related to two proportions. This might be a good time to take a break. Two proportion procedures are covered in section 6.3 of the Lock 5 textbook. You may want to go through the Wiley Plus questions associated with that section before moving on. Next, I'll go through the same procedures for two independent means. This content is covered in section 6.4 of the Lock 5 textbook. Our first learning objective for two means is to identify when the t-distribution may be used. In order to use the t-distribution, either both samples need to be large, so at least 30, or we need to know that in the populations, the variable is normally distributed. I've made this flowchart to help demonstrate this. The first question you should ask is, are the sample sizes both at least 30? If yes, then you can use the t-distribution. This is most often the case. But if one or both samples are less than 30, you need to ask a second question. Are the populations normally distributed? If yes, then you can use the t-distribution. If no, then you should use the bootstrapping or randomization methods that we covered in lessons 4 and 5. Assuming that the assumption for using the t-distribution is met, this is the formula for the standard error for the difference in two independent means. It's the same formula for confidence intervals and test statistics. Note that this formula uses s squared, which is the variance. Most of the time, you've been working with s, which is the standard deviation. Pay special attention when you're working through the homework as to whether you're given s or s squared. If you're just given s, you'll need to square it in this equation. I'll walk through one example. Here we have descriptive statistics for two independent groups. The control group, which we'll call group 1, and the treatment group, which we'll call group 2. I plugged these values into our formula. Note that in the descriptive statistics, we were given the standard deviation, which is s, so I had to square it. The standard error for the difference in these two means is 0.879. Next, we're going to construct a confidence interval to estimate the difference in two means. I'll do an example by hand using summary data. Then I'll take you to Minitab Express to walk through two examples there. We're using the same general form of a confidence interval. The sample statistic is the difference in the sample means. The multiplier, assuming assumptions are met, will come from a t-distribution. And the standard error is the formula that we just practiced. The example that I'll do by hand is the same one that we just worked through for computing the standard error. We're given these summary statistics, and we're told to construct a 95% confidence interval. The sample sizes are both at least 30, so we can use the t-distribution method. We have all of the values that we need here except for the t multiplier. I'll take you to Minitab Express to find that value. Recall that the t-distribution does vary depending on degrees of freedom. For two means, we'll be estimating the degrees of freedom as the smaller sample size minus 1. Note, this is different from the method that Minitab Express uses, so your answers may not always match exactly. Here, the control group has the smaller sample size of 45. Our t-distribution will have 44 degrees of freedom. I'll take you to Minitab Express now to find our t multiplier. I'm going to construct a probability distribution plot to display a probability. We have a t-distribution with 44 degrees of freedom. We want to find the values that separate the middle 95% from the outer 5%. We have equal tails with 5% or 0.05 split equally between the tails. Our t multiplier is 2.01537. Now we have all of the values that we need to plug into this equation. I am 95% confident that in the population, the mean of the control group minus the mean of the treatment group is between negative 2.772 and positive 0.772. Next, I'll show you how to compute this same confidence interval in Minitab Express by entering these data as summary statistics. I'm on a PC, so I'll go to Statistics, to Samples, T. If you're on a Mac, you'll go to Statistics, to Sample Inference, T. The default is to have raw data with both samples in one column. In this example, we have summarized data. Sample 1 was the control group. The sample size was 45 with a mean of 15 and sample standard deviation of 4. Sample 2 was the treatment group. The sample size was 60 with a sample mean of 16 and standard deviation of 5. Under Options, the default is a 95% confidence interval, so we do not need to change anything here. Click OK. Our 95% confidence interval is negative 2.7430 to positive 0.7430. This is just slightly different from what we found when we computed this interval by hand. That is because Minitab Express is using a different method for computing the degrees of freedom. The method that we used of taking the smaller sample size minus 1 is more conservative, which is why we ended up with a wider confidence interval when we did this by hand. For this example, Minitab Express uses 102 degrees of freedom, which resulted in a slightly smaller t multiplier and narrower confidence interval. This is something to be aware of if you're doing questions in Wiley Plus or working through textbook questions, because the textbook uses the more conservative estimate of degrees of freedom of the smaller sample size minus 1. Next, I'll do an example using raw data. The data set that I'm going to use comes from the Lock 5 textbook. You can find it on their website. It's called Student Survey, and you'll want the MTW file. I want to construct a 95% confidence interval to estimate the mean difference in heights of females and males. I'm on a PC, so I'll go to Statistics, to Samples, T. If you're on a Mac, you'll go to Statistics, to Sample Inference, T. The default is to have raw data, which we have. Sample is the response variable. That would be height. And sample IDs is the grouping or explanatory variable of gender. Under Options, we're constructing a 95% interval, so we don't need to make any changes here. Click OK. Pay special attention to what Minitab Express is calling Group 1 and Group 2. It tends to do this in alphabetical order, so here, females are Group 1 and males are Group 2. We're estimating the population mean for females minus the population mean for males. On average, females are shorter, so our confidence interval is completely negative. I am 95% confident that in the population, the mean for females minus the mean for males is between negative 5.8161 inches and negative 4.4861 inches. Now, let's move on to hypothesis testing. We'll be using the same 5-step hypothesis testing procedure. Step 1 is to check assumptions and write hypotheses. This is our flow chart for checking this assumption. Both sample sizes need to be at least 30, or the populations need to be normally distributed in order to use the t-distribution method. And that's the method that we're focusing on this week. To write our hypotheses, this chart comes from the online notes, and it shows all of the possible hypotheses. Note that these could also be formatted like this. Step 2, compute the test statistic. This is our formula. In the numerator, we have the sample statistic, which is the difference in the sample means, and in the denominator, we have the standard error. Step 3, determine the p-value. This is the area under the t-distribution that is more extreme than the test statistic in the direction of the alternative hypothesis. We'll need to use Minitab Express to look up this area. The degrees of freedom for that t-distribution will be the smaller sample size minus 1. Step 4, make a decision. If the p-value is less than or equal to the alpha level, which in most cases is 0.05, we reject the null hypothesis. If the p-value is greater than the alpha level, we fail to reject the null hypothesis. And step 5, state a real-world conclusion. If you reject the null, the results are statistically significant and there is evidence of a difference in the population. If you fail to reject the null, the results are not statistically significant and there is not evidence of a difference in the population. Let's walk through some examples. First, I'll do an example by hand. Then I'll do 2 examples in Minitab Express, one with summary data and one with raw data. Here's our research question and summary data. Do the average quiz scores differ for students in the morning and afternoon sections of a course? Step 1, check assumptions and write hypotheses. Here's our flowchart. The first question we ask is, are the sample sizes both at least 30? Our sample sizes are 35 and 40. Both are at least 30. This assumption is met and we can use the t-distribution method. Next, we write hypotheses. When comparing 2 means, the null is always that the 2 population means are equal. I'll write this as mu sub 1 equals mu sub 2. You could also say that mu sub 1 minus mu sub 2 equals 0. We want to know if scores differ for the 2 groups. We're not given a specific direction or any information about which group should score higher, so this is a two-tailed test. Our alternative hypothesis is that mu sub 1 does not equal mu sub 2. Step 2, compute the test statistic. Here's our formula. We have all of the values that we need in our summary table. We plug these values into the formula, and we get a test statistic of t equals 2.422. Step 3, determine the p-value. This is a two-tailed test, so the p-value will be the area in the left and right tails combined that are more extreme than our test statistic of 2.422. Recall that t-distributions vary depending on degrees of freedom. Our smaller sample size was 35, giving us 34 degrees of freedom. I'll take you to Minitab Express now to construct this t-distribution to determine the p-value. I'm going to construct a probability distribution plot to display a probability. We're constructing a t-distribution with 34 degrees of freedom. Our test statistic is a specified x value, and this was a two-tailed test. Our test statistic was 2.422. Click OK. Our p-value is the area in the two tails combined. 0.010 plus 0.010 gives us a p-value of 0.020. Step 4, make a decision. Our p-value is less than the standard 0.05 alpha level. We reject the null hypothesis. Step 5, state a real-world conclusion. There is evidence that the average quiz scores differ for students in the morning and afternoon sections of this course. Next, I'm going to take you to Minitab Express to show you how you could work through this same example there. I'm on a PC, so I'll go to Statistics, 2 Samples, T. If you're on a Mac, it's Statistics, 2 Sample Inference, T. The default is to have raw data, but here we have summarized data. Sample 1 will be the morning students. The sample size was 35. The sample mean was 14, and the standard deviation was 4. Sample 2 is the afternoon students. The sample size was 40. The sample mean was 12. And the sample standard deviation, 3. Under Options, the default is a two-tailed test, which is what we want in this case. Recall the research question was, do the average quiz scores differ? Click OK. If we were doing this hypothesis test from the very beginning, step 1 will be to check assumptions, so to check that our sample sizes are sufficiently large. We can do that here in the descriptive statistics. Then we would write our hypotheses, which Minitab Express does when it gives us the hypothesis test results at the bottom. Step 2, determine the test statistic. Our t-test statistic is 2.42. Step 3, determine the p-value. That's 0.0184. Step 4, make a decision. The p-value is less than the standard 0.05 alpha level. We reject the null. And step 5, state a real-world conclusion. There is evidence that the average quiz scores differ for the students in the morning and afternoon sections of this course. Let's do one more example, this time using raw data. I'm going to use a data set that comes with the Lock 5 textbook. You can find this on their website. It's called Student Survey, and you'll want the MTW file. Our research question is, do males and females differ in terms of how much they exercise each week? The variable labeled exercise gives us the number of hours per week the individual reported that they exercise. Again, I'll go to Statistics, to Samples, T. Now, we do have raw data, and both samples are in one column. The samples variable is the response variable, in this case, exercise. The sample IDs are the groups or the explanatory variable, in this case, gender. Under Options, we are conducting a two-tailed test because we want to know if males and females differ. We're not given a specific direction or specific hypotheses. Click OK. Step 1 of the 5-step procedure is to check assumptions and write hypotheses. In order to use the t-distribution method, we need to have sample sizes that are at least 30. Here, we had 168 females and 193 males, so the assumption is met. Down here, Minitab has written the hypotheses for us. Step 2, determine the test statistic. Our t-test statistic is negative 2.98. Step 3, determine the p-value. That's 0.0031. Step 4, make a decision. Our p-value is less than the standard 0.05 alpha level. We reject the null hypothesis. And step 5, state a conclusion. There is evidence that in the population, the mean number of hours per week exercised differs for males and females. We have just covered all of the learning objectives for this lesson. There are additional examples in the online notes. As always, if you have any questions, please post them to the Lesson 9 discussion board in Canvas.